Hi everyone. Today we're going to be asking ourselves an interesting question. The question is whether compound interest is in fact better than simple interest. So let's get the terminology right first. First of all, we have what is called the principal. And the principal is what you start with. So it's the starting money. And we're going to assume that it's greater than zero, so you're not starting with zero. The second thing, which is actually more important than the principal for compound interest and simple interest, is the interest rate. So sometimes it's written like 5%, but we're going to write it as 0.05. So we're going to say that the rate is equal to R, and in terms of percentages, it'll be 100R. But we're going to focus on R, so in decimals, because it's going to make our expressions easier to comprehend later. And we're going to assume that this is greater than -1. If it's less than -1 or -1, you lose all your money. So we're going to assume that it is greater than -1. But even any negative rate really is unreasonable, although a few banks have done it in recent years. If you want, you can just assume that R is positive or non-negative, but this is going to work for any interest rate greater than -1. Now let's actually look at what simple interest is. It says that if the rate is R and the principal is P and the time period, say like we're going to call one time period equal to 1 year, but it can be any time period. So time period, the number of time periods is T, so the number of years, or if your time period is a month, then the number of months. If these are the variables, R, P, and T, then what you do is that you start with your principal and you add the principal times the rate, and again you add the principal times the rate, and you do that T times. And what that gives you is P plus PRT, and that gives you the formula for simple interest, which is 1 plus RT. So that's the formula for simple interest for these variables. Let's look at compound interest now. The rate is going to be R. The principal is going to be P, and the number of time periods is going to equal T. But there is one more thing in compound interest, which is number of compoundings per time period. And I'll show you what that means in just a second, but we'll call that N. So here's how compound interest works. There are two components. One is that we divide the rate by N. So we get R over N is the rate. And so that's a sort of pull in a downwards direction of the amount of money that you get back. However, there is an upshot, and the upshot is that we compound N times. So this is advantageous to the receiver because you're compounding several times. And I'll show you now exactly what I mean by these two things. What I mean is that you have your principal and you multiply by 1 plus r over n. And then you multiply that several times, n times, 1 plus r over n. So you do that n times, and then you repeat this for each time period, so it's to the power of t, and that equals to p times 1 plus r over n to the power of nt. So let's compare the two expressions that we have. We've got p times 1 plus rt. That's a simple interest formula. And we've got this expression for the compound interest formula. And we want to know which one is bigger. So traditional wisdom says the compound interest is better. So what we're going to try to prove is that p times 1 plus r over n to the power of nt is strictly greater than p times 1 plus rt. Remember, we said that p is greater than 0, so we can cancel out the p's from both sides. We're doing some backwards work now. So we're going to rewrite this as 1 plus r over n to the power of nt is greater than, and I'm going to rewrite the rt in a slightly different form. We get 1 plus r over n to mimic what we have here times nt. So the two n's cancel out and we still have rt. So it looks like we have a couple of block variables here. We've got r over n and we've got nt. Let's replace these with variables. So we'll say x equals to r over n, which we know is greater than negative 1 over n, which is also greater than negative 1. And we're going to say m is equal to n times t. And we're going to have to put a restriction on these variables, but what I want to tell you is that this ends up becoming 1 plus x to the power of m is greater than 1 plus mx. And for those of you who've seen Bernoulli's inequality, we actually have a video on this that we posted earlier. This is Bernoulli's inequality. And it holds for x greater than negative 1. Actually, it works for x equal to negative 1 as well. And m is an integer greater than or equal to 2. So remember, I said there's going to be a restriction on what m is. We need m to be greater than or equal to 2. So what we're going to say is the number of compoundings in a time period is greater than or equal to 2, and the number of time periods is greater than or equal to 1, so that m equals to nt is greater than or equal to 2, which is what we need in order to apply Bernoulli's inequality. So by Bernoulli's inequality, it is in fact true that compound interest is strictly better than simple interest, assuming that we compound at least twice in a time period and that we have at least one time period. But this brings up a second question. And the question is more compoundings better than fewer compoundings? Let me write that down. Is more compounding better than fewer? So let's look at what this would mean. We want to show that if m is greater than n, and they're both integers, and by more compounding I mean a higher number of compounds in a time period. So if m is greater than n, then we want to prove 1 plus r over m to the power of mt and times the principal is greater than the principal times 1 plus r over n to the power of nt. Now again, we can get rid of the p's and we can take the root of t to get rid of the t's. So what we really want to prove is m greater than n implies, and m and n are integers greater than or equal to 2. We have 1 plus r over m to the power of m is greater than 1 plus r over n to the power of n. What we're going to do is that we're actually going to prove it for m equals to n plus 1, and that's going to mean we can apply it repeatedly. So let me show you what I mean. We'll say a compound of let's say k is equal to 1 plus r over k to the power of k, and we're going to show that ck plus 1 is strictly greater than c of k, assuming the rate is not 0, and you'll see why it can't be 0 in just a moment. And that's going to lead to ck less than ck plus 1 less than ck plus 2 and off to infinity. In fact, you can start with c of 2 and move up from there. So let's prove this. What we want is that 1 plus r over n plus 1 to the power of n plus 1 is greater than, well, let's say greater than or equal to for now. We'll show exactly when equality holds in just a moment. 1 plus r over n to the power of n. And we're going to rewrite the left side as n plus 1 plus r over n plus 1, and we're going to take the root of n plus 1 and put it over here. So we get 1 plus r over n to the power of n, and we're taking the n plus 1th root, and then we're going to rewrite this again in a different form. We're going to write it as 1 plus n times 1 plus r over n plus 1. So you see we have a sum of 1 and n of these divided by n plus 1. And we can rewrite the right side. For those of you who know the AMGM inequality, you'll see what I'm getting at. 1 plus r over n to the power of n root n plus 1. And this is simply the AMGM inequality. So for those of you who haven't seen AMGM before, let me write it for you. It says that a1 plus a2 all the way through to let's say ak divided by k is greater than or equal to a1 times a2 all the way through to ak root k. And you can see that what we have up here is a1 equals to 1 and a2 all the way through to an plus 1 is equal to 1 plus r over n. So this inequality certainly holds, but we want to prove a strict inequality, which means we need to figure out when equality holds. And equality holds if and only if a1 equals to a2 all the way through to an. And in this case, that means 1 equals to 1 plus r over n, and that's true if and only if r equals to 0. So as long as your interest rate is not 0, then we have a strict inequality, which says that c of k plus 1, we had it up here, is strictly greater than c of k. And so this proves that as long as your interest rate is not exactly 0, that more compounding will leave you with more money. Okay, thank you for watching, and I'll see you next time.